Okay, I'm doing one more video. If you haven't watched the product rule and the quotient rule videos, both of those, go ahead and do those first so you understand what I'm referencing. The purpose of this video is to look at a couple examples that look more complicated and to discuss what our best strategy is, because we don't want to waste a ton of time doing algebra, but the product rule and the quotient rule are considerably more complicated and therefore easier to make mistakes when applying them. So I do try to avoid them whenever possible. Now, I have had students disagree with me, and they use the quotient rule all the time, and they're more successful with it. So this isn't like you have to do this. You could essentially use the quotient rule when you have a function like 1 over x, just to give you an example. Okay, on Friday, we looked at rewriting this as f of x equals x to the negative first, so that we could then apply our power rule. And our power rule gave us f prime of x equals -1 times x to the negative second, or -1 over x squared. Okay, how would be another way of getting this answer? Well, as I just said, we could use our quotient rule. So if we use our quotient rule, our derivative becomes the denominator times the derivative of the numerator. Remember, derivative of 1 is 0, minus the numerator times derivative of the denominator, which is 1, all over denominator squared. So you can see that we did derivative here and derivative of there. And now if I simplify that, I have x times 0. Well, x times 0 is just 0, so I don't need that. I have a -1 times 1, which is 1 over x squared. And that is indeed the same answer that we got a minute ago. So it's really just a matter of opinion here. But I wanted to show you that you can use it in any case. Basically, if you have a constant in the numerator, which is what we have here, we don't have to apply the quotient rule. The quotient rule has to be applied when you have a quotient of two functions, function in the numerator, function in the denominator in terms of some variable. Okay, but it can be, you'll probably see here that what's going to happen is you're always going to get this term that's going to be 0. And that's why we essentially don't need to apply it. Okay, but it is an option. Let's take a look at a couple more examples that are a little more complicated. So here's a function for us to consider. Y equals x cubed minus x all over x. So definitely have a quotient of two functions. The question is, does it have to be a quotient of two functions, or can I simplify it? So we're going to apply some algebraic tricks here, and we're going to rewrite this function as a difference of two functions. So again, this is backwards from how we normally use how we normally do things. Instead of combining fractions, we're separating our fractions all over the same denominator. I always like to ask myself, can I legitimately combine these and get back to here? And the answer is yes in this case, so we're good. And I'm going to go ahead and keep simplifying here. Y equals x cubed over x would really just be x squared, and x over x would be 1, and voila, I've simplified my function. I no longer have a product or a quotient of two functions, and now I can go ahead and do y prime is equal to 2x minus 0, or just 2x, and I'm done. Okay, just for fun, because I like to show that things can work multiple ways. Let's go ahead and do it the other way. So let's go ahead and take our original function as is, and let's apply our product or quotient rule and see what we end up with. So we're going to end up with denominator times derivative of the numerator. Notice I'm not writing everything out as much this time, so I'm just going to take some shortcuts here. 3x squared minus 1, so that's me doing the derivative right there, minus numerator, which is x cubed minus x, times derivative of the denominator, which is 1, all over denominator squared x squared. Okay, I'm going to simplify that a little bit. Whoops. So my numerator, again, I'm going to just keep the denominator as is, work out the numerator, 3x cubed minus x cubed plus x all over x squared. That's going to simplify to a 2x cubed minus x plus x is going to cancel out, so I actually don't have this minus sign. All over x squared, and simplifying that, I get 2x, same thing that I got a minute ago. Okay, so it really is your choice. I tend to think that the first way I did this problem was a little bit easier, simplify first. Example I want to do with you, and that's going to be something that looks pretty ugly. Let's consider the function y equals numerator quantity x squared minus 2 times quantity x squared plus 5x minus 1 all over x cubed. And this one is going to be really ugly if we try to do our quotient rule, because if you just take a minute and look at it, what's going on here, we've got a situation where we have a product of two functions inside of our numerator. So if you're considering my quotient rule, it's going to be denominator times derivative of the numerator. Insert product rule as you're doing derivative of the numerator. Then continue with your quotient rule, which would be minus numerator times derivative of the denominator all over denominator squared. There's a lot of potential for error in that. So this is a case where I would say probably worth our time, even though I don't want to waste time doing algebra, probably worth our time to do a little algebra here and simplify the numerator. So if I go ahead and do that, again, I'm not doing y prime, I'm just doing y equals, I'm rewriting, and I'm going to go ahead and multiply my polynomials there, my binomial times a trinomial right here. So if I do that, I'm going to end up with, let's see, x to the fourth plus 5x cubed minus x squared minus 2x squared, minus 10x plus 2 all over x cubed gives me x to the fourth plus 5x cubed minus 3x squared minus 10x plus 2. Wow, that's a lot of terms. All over x cubed. And then hopefully you're starting to recognize, again, I'm trying to get you to look at this and kind of think about options here. Yes, we have a quotient of two functions, but if I take that, since I have this simple denominator, if I take that and rewrite it, I can rewrite it as sum or difference of a lot of terms, all separate, because I can put them all over x cubed. So I'm going to give myself some more room here, and I'm going to rewrite that once more. This time it's going to be y equals x to the fourth over x cubed plus 5x cubed over x cubed minus 3x squared over x cubed minus 10x over x cubed plus 2 over x cubed. That becomes x plus 5, cancel, minus 3 over x minus 10 over x squared plus 2 over x cubed. And here's a good chance for us to review how do we do something like this. I'm guessing the first two terms look good to you and the next two do not look so good. So in order to take the derivative, we're going to rewrite in a way that looks nice to us. So I'm going to rewrite this negative 3 over x to a 3x to the negative first. And I'm going to rewrite my 10 over x squared to a 10x to the negative second. And I'm going to rewrite my 2 over x cubed to a 2x to the negative third. I'm going to keep the first two terms as is, so x plus 5. And now I'm finally, at this point, ready to take the derivative. So y prime, or dy dx, equals 1 plus derivative of a constant is 0 minus, actually it's going to be plus 3 times negative 1, so 3x to the negative second minus 10 times a negative 2, so that'd be plus 20x to the negative third. And then bring the negative 3 out front, multiply by the 2, so minus 6x to the negative fourth. And we're just going to tidy that up for my final answer of 1 plus 3 over x squared plus 20 over x cubed minus 6 over x to the 4th. And remember, my rule is no negative exponents. I'm okay with pretty much anything else, but we're not going to leave negative exponents. That is not considered nice algebraically. We started with positive exponents, so let's finish it that way. So that's going to be my final answer. Hopefully that's enough examples. If you get stuck on anything else in my math lab, I tried to give you a variety and kind of hit the highlights, but if you get stuck on anything, let me know. I can make an additional video to help you out.